This method is called iteration method. In this method, we need to write. We are asked to obtain the root of this equation. Then we write this f of x equal to 0 as rewrite this equation as x equal to phi of x. Okay, we write equation as x equal to something. Okay, it's x equal to a function of x itself. Okay, if once you write this, then you can easily find out the first approximation. We already discussed how to find out the first approximation. So once you got the first approximation by taking a and b with f of a is less than 0 or vice versa, f of b greater than 0, or you can expect f of a is greater than 0, f of b is less than 0. In this case, x naught is equal to a. In this case, x naught is equal to b. If b is f of b is less than 0, then this is taken as the first approximation or the initial approximation. Then you can get this x1 as phi of x naught, and x2 can be obtained by considering phi of x1, and x3 can be obtained using phi of x2, and so on. Okay, so these are the best approximations for the roots of this f of x. Okay, so the only thing you need to remember is if you write if you are given a function f of x, then there are several methods to write this x equal to phi of x, but you need to remember that phi dash of x should be less than 1 to carry out this iteration method. Okay, then only these x1, x2, x3 tends to or will give the root of this equation. Okay, so however this phi dash of x, the modulus of that should be less than 1. Okay, how much this is small, then the convergence of these x1, x2, x3, that means this rapidly give the solution of this f of x equal to 0. Okay, now we can discuss the example for this method. This is the example for iterative method or iteration method. So first of all, you need to find out two consecutive integers. So if we start trying with 1, and that is f of 1 is 1 minus 1 minus 1, that is equal to minus 1, that is negative. And f of 2, if you evaluate 8 minus 2 minus 1, that is 6 minus 1, that is 5, that is greater than 0, then you can fix that f of 1 and f of 2 are opposite signs. Then you can get this 1 and 2, that means f of x equal to 0 as a root in between 1 and 2. So these are the two numbers, but f of 1 is negative, f of 2 is positive, so we take initial approximation as x1. We can denote it as x0 or x1 as 1. Okay, so if you write this, then rewrite this equation as x cube is equal to x plus 1. We rewrite this equation as x cube is equal to x plus 1, or you can write this x equal to x plus 1 whole to the power 1 by 3. Okay, x plus 1 whole to the power 1 by 3, then this is denoted by phi of x. So our phi of x is x plus 1 whole to the power 1 minus 3. So our initial approximation is 1. So just verify that phi dash x. What is phi dash x here? Phi dash x is obtained by 1 by 3 times x plus 1 by 3 minus 1. 1 by 3 minus 1, that is equal to 1 by 3 x plus 1 raised to minus 2 by 3. Okay, now you just evaluate this phi dash x at x equal to 1, x1 at x equal to 1, that is phi dash of 1. Okay, this is in fact our intention is to evaluate phi dash of x1 that is modulus of phi dash of 1. What is phi dash of 1? Phi dash of 1 is equal to 1 by 3 times 2 to the power minus 2 by 3. Okay, that is equal to 0.21. Just evaluate this using a calculator, then you can get this value is less than 1. Okay, therefore you can write this, or you can take this phi of x to carry out the iteration method. Okay, so if you are setting x1 first, then you need to evaluate modulus of phi dash of 1. Okay, then this value is less than 1, then you can easily carry out the iteration method. That is, to evaluate x2 you need to evaluate phi of x1. That is, if we already write what is phi of x. Phi of x is this one, x plus this is phi of 1, x1 is 1 here. Then what is phi of 1? That is 1 plus 1 whole raised to 1 by 3, that is 2 raised to 1 by 3, that is equal to 1.26. you just evaluate this with a calculator. Then now you can easily verify x. You can easily find out x3. You need not verify this equation. This equation will be verified only once in the beginning of the iteration method. That means this equation is verified only for x1, for the first approximation. Okay, now you can find out x3, that is phi of x2. We can get we could get this x2 as 1.26, then phi of 1.26, that is 1.26 plus 1 whole to the power 1 by 3. This is the expression. Then that will be 1.312. This is x3. Similarly, you can find x4. What is x4? That is phi of x3. What is phi of x3? Phi of 1.312. So using calculator, evaluate 1.312 plus 1 whole to the power 1 by 3. So that will be 1.322. 1.322. And observe that these two places, if you observe this, then by rounding off to two decimal places, you can get this is 1.31, this is 1.32. And next we write x5. What is x5 here? That is phi of x4. You can get the value of this as 1.324, and you compare this with this, then you can get that those two values are the same. Then you can get 1.32. Okay, these two values are the same. Then you can get these are the this is the x raised to 5 is the root of the equation, 1.32 is the root. Okay, so this is the way we evaluate the root of the equation using iteration method. Okay, now we continue discussing our the solutions of the methods for finding the solutions of algebraic and transcendent equations. So this is in the last class we have discussed iteration methods. This is its consequence. It's called Newton's iteration method or Newton-Raphson method. Mostly this is known as Newton-Raphson methods. Okay, so we if you take the first approximation x naught as the approximate root, that means if you have a real root alpha in between some a and b, then you can take one of these values as the initial approximation. So once you obtain this initial approximation, you can evaluate the iteration formula as xn plus 1 is equal to xn minus f of xn divided by f dash of xn. Okay, so this is the iteration formula. This value is for n is equal to 0, 1, 2, 3, etc. So and this where this f of x equal to 0 is our required equation to find the solutions of this equation. F of x equal to 0, we need to perform this iteration. Okay, so this is what we called a Newton-Raphson formula or Newton-Raphson method to evaluate the solutions of approximate solution of the tangent law uh, algebraic equation. So now once you understand this formula, we have three remarks. The first one is the geometrical interpretation of this formula. Okay, interpretation. What is the meaning of this formula? To get the geometric interpretation, so you consider this function y equal to f of x, and alpha is its corresponding root, or 0, this is actual 0. So if you take the first approximation as x naught, then this point can be denoted as x naught comma f of x naught. Now you consider the tangent at this point. Okay, so this tangent meet at this point, and how do you get this point? That's the first thing, and this point is considered as our x1. So how will you get this x1? So first of all, you need to write the tangent of this this curve at this point. Okay, tangent of y equal to f of x. So that is obtained by y minus y naught, equation of the tangent. This equation of this line is obtained by considering the line passes through this point x naught f of x naught. This is nothing but our y naught, so it passes through x naught y naught. Then the equation of the line will be f of y minus y naught into slope into x minus x naught. Then what is the slope? Slope is the derivative of f at this point, so the f dash of x naught, that is the slope here. So this is slope of the tangent at this point. Okay, so now this this y naught is nothing but f of x naught. Okay, so y minus f of x naught equal to f dash of x naught times x minus x naught. So this is in fact the equation of the tangent of this curve y equal to f of x passing through this point x naught f of x naught. Okay, so in order to get this point, we need to put y equal to 0 here, because in order to get the point of intersection of this tangent and x-axis, that is obtained by y equal to 0, because at on the real line we have y equal to 0. So when you put this value y is equal to 0, then this takes the form minus f of x naught is equal to x times f dash of x naught minus x naught times f dash of x naught. Okay, so this is the value of x1 is this. So we need to replace this x by x1. Then you will get you can easily get x1 from this equation. This x1 will be we can solve for this x1. Then that will be x1 times f dash of f naught f dash of x naught equal to, this will be equal to x naught times f dash of x naught minus f of x naught. Okay, so this x1 will be x1 takes the form x naught minus this f of x naught divided by f dash of x naught. So using this equation, using this value of x naught, you can get the value of x1. Okay, similarly you consider x1 here, and you can get the point x1 comma this point is x1 comma f of x1. Then using the same argument, you can get by considering the tangent here, then this point will be x2. Okay, so the x2 takes the form x2 is equal to x1 minus f of x1 divided by f dash of x1. So we can generalize this formula as x of xn plus 1 is equal to xn minus f of xn by divided by f dash of xn. Okay, so this is the geometrical interpretation of this this Newton-Raphson method. So when you repeat this process, you can get all these values x1 x2 converges to the actual solution. So that will give the real solution for this equation f of x equal to 0. In the next remark, we will discuss the rate of the rate of convergence or the condition for convergence, or you can write it as a condition for convergence. So for this we write it as not right, it is condition for convergence. This is the condition for convergence. This is obtained using the previous method, iteration method, such that mode phi of x is less than 1. So using this fact and this, when we consider this as our phi of x, then you can get this form, this condition. Okay, so this is the second remark. And finally we have the third remark, that is nothing but the rate of convergence. Okay, this is the condition for convergence. Next we will consider the rate of convergence, and that rate of convergence is defined as that is half, that is rate of convergence, in terms of this f and the derivatives of f, you can get the rate of convergence. Then rate of convergence is defined as half this k times epsilon n square, that is nothing but half of half f double dash alpha divided by f dash alpha times epsilon n square, that is epsilon n plus 1, where this epsilon n plus 1 is the error in the n plus 1 stage, that is the difference between alpha minus xn plus 1, that is the n plus 1 approximation, and difference between the actual roots and this n plus 1 approximation. Similarly, epsilon n is alpha minus this xn. So this is the rate of the convergence. That means the error follows this rule. That is the meaning of this. So this is the its rate is the subsequent rate will be the constant times. This is always fixed. This is independent of n. So this constant times epsilon n square. So this is the previous error. So the subsequent error will be the square of the previous error. So this is this Newton-Raphson method has a quadratic convergence. In other words, we can say its order of convergence is 2 due to this factor. Okay, so this is three remarks on this Newton-Raphson method. Now we will discuss a problem which illustrates the Newton-Raphson method. So this is the example. Find the real root of the equation x raised to 4 minus x minus 9 equal to 0. So first of all, we need to get the initial approximation. So first we evaluate f of 1. You just evaluate f of 1, then you will get the value as minus 9. You can cancel first two terms, 1 minus 1, that is 0. And next we evaluate f of 2. F of 2 is a positive quantity, that is 5, that is 16 minus 2 minus 9, that is 5. Since this f of 2 is less than the also f of 2 is we can consider this f of 2, the modulus of f of 2, that is 5, which is less than modulus of f of 1. You can get you can take the initial approximation or first approximation as or x1 or x0 as 2. So using this Newton-Raphson method, we evaluate x2. For that we evaluate f dash x. What is f dash x? That is 4x cubed minus 1. Okay, so this is the derivative of this function. Now you evaluate x2. How will you evaluate x2? The formula is x2 is equal to x1 minus this f of x1 divided by f dash of x1. Now you substitute the values for this x1 and f of x1. You can get this x2 is equal to what is x1? X1 minus, we write the first, we evaluate the formula. that is x1 minus this f of x1 is obtained from this x1 raised to 4 minus x1 minus 9. This is f of x1 divided by f dash x1, that is 4 times x1 cube minus 1. Okay, now you can simplify this, that will give 3 times x1 raised to 4 plus 9 divided by 4x1 cube minus 1. 4x1 cube minus 1. So now substitute the values for x1 and x1 in numerator and denominator. You can get that is 3 times 2 raised to 4 plus 9 divided by 4 times 2 raised to 3 minus 1. That will give the value is 57 by 31, that is 1.8. You can evaluate this using a calculator. So you will get the second approximation, x2. So using this x2, you can evaluate x3. Then you will get x3. Use the same procedure. So x3 will be, you can get x3 will be 1.8.81, and x4 will be 1.813. Then x5, the similar fashion you can evaluate x5 using x4. So that will be that quantity is again 1 point, the x4 will be 1.813. So from this you can write the you need not worry about x5, or you follow this procedure and try to find out the solution correct up to 3 decimal place. So you continue this process, and if you got to consecutive approximations for which these first 3 places are the same, then you can conclude with that answer. Okay, so this is the value of this is the root of our function equation f of x equal to 0. Okay, so this is the way we use the Newton-Raphson method to evaluate the roots of the equation. Thank you.